Hello. Yeah, in this video, I will show you how to test the assumptions of ANOVA. As you know, ANOVA has several assumptions, such as the normality of the data, equivariances, and independence of the data. First, let's reading the data set. We use the built-in R package data sets. Load that in. And we get the ARIS data set. So you can see there are 4 continuous variables, and there's a factor species. So first, let's fit an ANOVA model for sepal dot length, and the group is a species. We can fit an ANOVA model using the R function AOV. And here's the summary of the model. So you can see the ANOVA table is generated there. For testing assumptions in ANOVA, in this video, I'll show you how to use the library called CAR, to do different tests. First, let's load in the library CAR. And for testing the normality of the data, first we calculate residuals using the residual function. And then we use the Shapiro test. So it's a Shapiro dot test for the M1 residual. Okay, so in this data set, the p-value from Shapiro-Wilk normality test is 0.21. So the normality assumption reasonably met by this data set. Okay. Next one is test the equivariance assumption. And there's a Levine test function in the library CAR we can use to test equivariance. So the syntax is very easy. It's a Levine test of M1. The p-value is very small, so the variances are not equal. So that's the test result. So in this video, I will not discuss how to fix that. Okay, so this is just for testing. Next one, we want to test independence of the data. So we can use the Durbin-Watson test of M1. The Durbin-Watson test is developed for testing time series data. So here we borrow this test from time series analysis for the data we have. So we kind of view the data we have it as a sequence of data points as a time series. Okay. So the p-value is 0.974. So it's, really the data are not correlated, so they're independent if they're normally distributed. Right? And then we have another test for outliers. So outlier test of M1. You can see the unadjusted p-value is very small. So there's some concern about outliers. But then we have the Bufferoni adjusted p-value is 0.117. So we can say, well, maybe we can get away with saying, okay, there's no outliers that cause serious concern, so something like that. Okay. The last point I want to make is just remember ANOVA is a special case of linear regression. So all the tools for linear regressions can be applied for ANOVA. Okay, for example, remember the default residual plots of a linear regression model fit object using the R function plot. We can do that for ANOVA model. So we can split the graphic window into 2 by 2. And we can plot it. You can see there's the 4 plots. So you can look at the equivariances, you can look at the normality, and the leverage plots. So this is just for additional examination of the assumptions of an ANOVA. Thanks.